Chapter 7 is about the distribution of sample means, more specifically about the connection between samples and populations. So let me begin again by telling you how this is connected to the previous chapters. In Chapter 5 and 6, we looked at the Z-scores and the probability. Whenever we have a score from a population, we can get a Z-score that describes exactly where that score is located in the distribution. If the population is normal, we are able to determine the probability value for obtaining an individual score. For example, we said in a normal distribution, any score that's located in the tail of the distribution beyond a Z-score of negative or positive 2 is an extreme value. And a score this large has a probability of only 0.0228. However, the Z-score and probabilities that we considered so far are limited to situations in which the sample consists of a single score. As you can imagine, most research studies have much larger samples, so your N might be 50 or 75 or 100 or even larger. In these situations, the sample mean, rather than a single score, is used to answer questions about the population. With Chapter 7, we extend the concept of Z-scores and probability to cover situations with larger samples. Specifically, we introduce a procedure for transforming a sample mean into a Z-score. So a researcher is able to compute a Z-score that describes an entire sample. Just like before, a Z-score near 0 indicates a central representative sample, and a Z-score beyond plus or minus 2 indicates an extreme sample. Here we learn that it is possible to describe how any specific sample is related to all the other possible samples. In addition, we can use the Z-score to look up probabilities for obtaining certain samples, no matter how many scores the sample has. After this chapter, you should be able to define the distribution of sampling means, describe a distribution by shape, the expected value and the standard error, and describe location of sample mean by a Z-score, and determine the probabilities corresponding to sample mean using Z-scores and the unit normal table. So again, we're reading the probabilities from that unit normal table. Let's look at the connection between a population and a sample. So here you can see we have the population, and then here we took a random sample from that population. The parameter, which remember is the value that describes the population, in this case represents the proportion of white respondents in the population. So in this population we have 15 white respondents and we have 25 total. So the proportion of white respondents in the population is 15 over 25, which is 0.60. We take a random sample. In this case we took 6 people from the population, and then the statistic, that is the value that describes the sample. In the sample now we have 4 white respondents over a total of 6. So you can see that the proportion of white respondents in the sample with 0.67 is very close to the actual parameter of 0.60. Important is that if we would take a correct sample, you can see that the proportion in the statistics is very close to the actual value. Therefore, if you correctly sample, you should be able to generalize or make inferences about the population. So if the sample is completely random, then the sample mean should be a good indicator of the population mean. Let's assume you take multiple samples from a population. So let's say you choose 200 households randomly and you get the information on how many minutes they spend on long distance phone calls a week. Then you get the mean of this first sample. Then you do another sample of choosing 200 households, and obviously they're going to be 200 different households than before. Again, you get the mean of the second sample and you do this sampling 100 times. So you will end up with 100 means. Here you can see we have 100 means from 100 household samples. Clearly, they all differ from each other. Even if a few are the same, most of them differ. if you take several samples, all the same size, from one population, the samples will have different means. Some will be above the actual population mean and some will be below. However, the distribution of sample means states that if all samples are the same size, then the mean of the sample means will equal the population mean. The distribution of sample means is a collection of sample means for all the possible random samples of a particular size, n, that can be obtained from a population. Sampling distributions are different because the distributions that we looked at in earlier chapters were distributions of scores from samples. So we had, for example, 7 people in our sample. So we looked at the 7 scores from our 7 people in that sample. However, the distribution of sample means is called a sampling distribution because it's a special kind of population. It is a distribution of sample means obtained by selecting all the possible samples of a specific size from a population. In reality, we do not take hundreds of samples just in order to generalize to the population. We normally only take 1 or maybe 2 samples. However, we can still derive a standard deviation of a theoretical sampling distribution as if we would do all these samples. And that's what's called the standard error of the mean, or sampling error. It describes how much dispersion there is in the sampling distribution of the mean. So error does not mean we made a mistake, but it is a natural discrepancy or the amount of error between a sample statistic and its corresponding population parameter, because 2 samples are very, very rarely identical. When the sample is sufficiently large, you can assume that the distribution of sample means is normal. This is just a characteristic of the distribution of sample means. And the distribution of sample means approaches a normal distribution when n, in this case the number of our samples, is large. So here you can see a frequency polygon for the different number of samples, right? So n is 2, n is 10, n is 25, so we're increasing the number of samples. And here you can see n is 100. So the distribution of sample means approaches a normal distribution the larger n gets. And this is the basis for inferential statistics. The central limit theorem applies to any population with a mean and a standard deviation. It states that the distribution of sample means approaches a normal distribution when n is large. It doesn't matter what the shape is, the distribution of sample means becomes more normal as the sample size increases. So what the theory concludes is that with a sufficient sample size, the sampling distribution of the means will be normal regardless of the shape of the population distribution. Even if the population distribution is skewed, the sampling distribution will be normal if we take large enough random samples. And also the theory assures that as the sample size gets larger, the mean of the sampling distribution becomes equal to the population mean. And when the sample size gets larger, the standard error of the mean decreases. Let's look at a short video with a nice explanation of the central limit theorem.
Concepts in statistics and maybe in all of mathematics, and that's the central limit theorem. Central limit theorem. And what it tells us is we can start off with any distribution that has a well-defined mean and variance, and if it has a well-defined variance, it has a well-defined standard deviation. And it could be a continuous distribution or a discrete one. I'll draw a discrete one just because it's easier to imagine, at least for the purposes of this video. So let's say I have a discrete probability distribution function, and I want to be very careful not to make it look anything close to a normal distribution because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say it can take on values 1 through 6. 1, 2, 3, 4, 5, 6. It's some kind of crazy dice that's very likely to get a 1. Let's say it's impossible. Let me make that a straight line. You're very high likelihood of getting a 1. Let's say it's impossible to get a 2. Let's say it's an okay likelihood of getting a 3 or a 4. Let's say it's impossible to get a 5. And let's say it's very likely to to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation, maybe it'd be that far and that far above and below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable that's described by this probability distribution function, I'm going to take samples of it, but I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. And when I say average, I mean the mean. So let's say, let me define something. Let's say my sample size, and I could put any number here, but let's say first off we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples from this. So let's say the first time I take 4 samples, so my sample size is 4. Let's say I get a 1, let's say I get another 1, and let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. And I know the terminology can get confusing because this is a sample that's made up of 4 samples. But when we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about over the next few videos, normally the sample refers to the set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily view one of these as a sample. But we're taking 4 samples from here. We have a sample size of 4. And what I'm going to do is I'm going to average them. So let's say the mean, I want to be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 6 is 11, 11 divided by 4 is, what, 2.75. 2.75. That is my first sample mean for my first sample of size 4. Let me do another one. My second sample of size 4, let's say that I get a 3, 4, let's say I get another 3, and let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is 0, so I can't have any 2s or 5s over here. So for the second sample of sample size 4, my sample mean for my second sample mean is going to be 3 plus 4 is 7. 7 plus 3 is 10. Plus 1 is 11. 11 divided by 4, once again, is 2.75. Let me do one more because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more, but let me just do one more in detail. So let's say my third sample of sample size 4, so I'm going to literally take 4 samples. So my sample is made up of 4 samples from this original crazy distribution. Let's say I get a 1, and a 6, and a 6. And so my third sample mean is going to be 1 plus 1 is 2, 2 plus 6 is 8, 8 plus 6 is 14, 14 divided by 4, 14 divided by 4 is what? 3.5. 3.5. And as I find each of these sample means, so for each of my samples of sample size 4, I figure out a mean. And as I do each of them, I'm going to plot it on a frequency distribution. And this is all going to amaze you in a few seconds. So I plot this all on a frequency distribution. So I say, okay, on my first sample mean was 2.75. So I'm plotting the actual frequency of the sample means I get for each sample. So 2.75, I got it one time, so I'll put a little plot there. So that's from that one right there. And I got the next time, I also got a 2.75. That's a 2.75 there, so I got twice. So I'll plot the frequency right there. Then I got a 3.5. So all the possible values, I could have a 3, I could have a 3.25, I could have a 3.5. So then I had the 3.5, so I'll plot it right there. And what I'm going to do is I'm going to keep taking these samples. Maybe I'll take 10,000 of them. So I'm going to keep taking these samples. So I go all the way to 10,000. I just do a bunch of these. And what's going to look like over time is each of these I'm going to make it a dot because I'm going to have to zoom out. So if I look at it like this, over time, still has all the values that it might be able to take on. 2.75 might be here. So this first dot is going to be, this one right here is going to be right there, and that second one is going to be right there. Then that one at 3.5 is going to look right there. But I'm going to do it 10,000 times because I'm going to have 10,000 dots. And let's say as I do it, I'm going to just keep plotting them. I'm just going to keep plotting the frequencies. I'm just going to keep plotting them over and over and over again. And what you're going to see is, as I take many, many samples of size 4, I'm going to have something that's going to start kind of approximating a normal distribution. So each of these dots represent an incidence of a sample mean. So as I keep adding on this column right here, that means I kept getting the sample mean 2.75. So over time, I'm going to have something that's starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit, and this was the case for, so in orange, that's the case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with a sample size of maybe 20. So in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my random variable, and I average those 20, and then I plot the sample mean on here. So in that case, I'm going to have a distribution that looks like this. And we'll discuss this in more videos. But it turns out if I were to plot the sample, 10,000 of the sample means here, I'm going to have something that, two things. It's going to even more closely approximate a normal distribution, and we're going to see in future videos it's actually going to have a smaller, well, let me be clear. It's going to have the same mean. So that's the mean. This is going to have the same mean. But it's going to have a smaller standard deviation. So I should plot these from the bottom because you kind of stack it. One you get one, then another instance, and another instance. But this is going to more and more approach a normal distribution. So the reality is, and this is what's super cool about the central limit theorem, as your sample size becomes larger, or you can even say as it approaches infinity, but you really don't have to get that close to infinity to really get close to a normal distribution. Even if you have a sample size of 10 or 20, you're already getting very close to a normal distribution. In fact, about as good an approximation as we see in our everyday life. But what's cool is we can start with some crazy distribution, right? This has nothing to do with a normal distribution. But if we have a sample size, this was n equals 4, but if we have a sample size of n equals 10, or n equals 100, and we were to take 100 of these instead of 4 here and average them, and then plot that average, the frequency of it, then we do take 100 again, average them, take the mean, plot that again, and if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that especially if we had an infinite sample size, we would find a perfect normal distribution. That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time, but you could have also taken the sample sum. The central limit theorem would have still applied. But that's what's so super useful about it. Because in life, there's all sorts of processes out there, proteins bumping into each other, people doing crazy things, humans interacting in weird ways, and you don't know the probability distribution functions for any of those things. But what the central limit theorem tells us is that if we add a bunch of those actions together, assuming that they all have the same distribution, or if we were to take the mean of all of those actions together, and if we were to plot the frequency of those means, we do get a normal distribution. And that's frankly why the normal distribution shows up so much in statistics, and why frankly it's a very good approximation for the sum or the means of a lot of processes. Normal distribution. What I'm going to show you in the next video is I'm actually showing you that this is a reality, that as you increase your sample size, as you increase your n, and as you take...
So this theory is important in showing us that the larger the size of the sample, the more closely the sample statistic cluster around the population parameter. And this is in fact what we want, right? Since we don't know the population, we take samples to estimate what the population looks like. We can conclude that the larger the size of the sample, the more closely the sample statistic clusters around the population parameter. And with sufficient sample size, the sampling distribution of the mean will be normal regardless of the shape of the population distribution. The mean of the distribution of sample means is a new symbol. It's mu with an m, and it has a value expected to the mean of the population of scores. Mean of the distribution of sample means is called the expected value of m, the expected value of the mean. You know that the variability of a distribution of scores is measured by the standard deviation. The variability of a distribution of sample means is measured by the standard deviation of the sample means, and that is what's called the standard error of m, and is written as this symbol, so sigma m. In journal articles or other textbooks, the standard error of m might be identified as standard error or SE or SEM, so this is not a universally accepted symbol. The standard error of m is the standard deviation of the distribution of sample means. It provides a measure of how much distance is expected on average between the mean of the sample and the population mean. By looking at the formula, you can see that as sample size increases, the size of the standard error decreases. So larger samples, the more accurate we are. Law of large numbers. The larger the sample size, the more probable it is that the sample mean will be close to the population mean. Population variance. The smaller the variance in the population, the more probably it is that the sample mean will be close to the population mean. The primary use of the distribution of sample means is to find the probability that is associated with any particular sample, with the sample mean. The proportion of the normal curve are used to represent the probabilities, and we just do that by calculating a z-score again for the sample mean and find the probability. And you can see in the formula now, it's very similar to the one we've been using, but instead of our score x, we now use the mean of the sample. And the standard deviation for the distribution of sample means is the standard error of the mean. And again, the sign is going to tell us whether the location is above or below the mean, and the number tells the distance between the location and the mean in standard deviation or standard error units. Let's look at an example. A sample is selected from a population with a population mean of 90 and a population standard deviation of 15. So the question is, find the z-score for the sample mean for the following sample. We have n, the sample n is n scores, and we have a sample mean of 100. Begin again by writing down what it is that you know. We know the population mean is 90, the standard deviation is 15 of the population. The sample size is n, and the sample mean is 100. And we are supposed to find the z-score for the sample. So we know we need the Z formula, the sample mean minus the population mean. Both of those are given, but we also have to find the standard error of the mean. So we need that formula. For that formula, so to solve for the standard error of the mean, we need the standard deviation, which we have from the population, over the square root of the number of people in the sample. So here at this point, we can just plug in. We get a standard error of the mean of 5. Now we can go back to our Z formula and just plug in the values. And we get a z-score of positive 2. Let's look at another example to a problem similar to what we've been doing in the last chapter. What is the probability of obtaining a sample mean greater than 60 for a random sample of 16 scores selected from a normal population with a population mean of 65 and a population standard deviation of 20? And begin by writing down what it is you know again. This is what we know. What is it that we're actually looking for? What is the question? We want to obtain a sample mean greater than 60. So let's do a rough draft. This is our normal distribution. So if we're looking for a mean of 60, we know the population mean is 65, then we know we're looking for scores greater than 60, that is everybody in this direction. So we need a z-score. We're writing down the formula. Here we know we need to get the standard error of the mean, so using that formula, and here we can just plug in again. So it's 20 over the square root of 16. We get a standard error of the mean of 5. Now we can plug this back into our z-score formula, and we get a z-score of -1. And you can see this is what we had visualized in the picture already, a z-score of -1. Now we can find the probability of obtaining sample mean greater than 60. For this we will need the normal unit table again. We look up a z-score of -1. And since we are going in this direction, we can see that it's in the body So the probability of obtaining a sample mean greater than 60 is 0.8413. Let us look ahead to inferential statistics. Inferential statistics use sample data to draw general conclusions about populations. But sample information is not a perfectly accurate reflection of its population due to sampling error. So due to that difference that always exists that we talk about. The differences between sample and population introduce uncertainty into inferential processes, and statistical techniques use probabilities to draw inferences from sample data. Please remember, if you have any questions about the equations, about the concepts, or any other questions, just send me an email. I'm here to help. Please practice your worksheets for this chapter. If you get stuck anywhere, look at my solution videos or send me an email. Congratulations, you reached the end of this chapter. Remember, if you have any questions, please email me anytime. Bye. See you next time.